Laoshi. So I'm from National University of Singapore. Today it's very nice to share our work about 3D Gaussian compression. So this work is collaborated with Simony and Geraldine from University of Toulouse. I'm very excited and proud of this work. So I actually prepared a lot of videos and slides so that I can share everything to you. So I will try to control the time, but for me, I exceed the time. Okay, so first, let's see what is 3D Gaussian representation. So all the things is about we want to compress 3D Gaussian, right? So the story starts with the point cloud. So basically, 3D.js is a kind of improvement for the point cloud. So this is what is point cloud, right? So Jun already introduced this to you. So point cloud is always my favorite 3D representation. So that's why I did my work in my first 2 years in my PhD. So I also have several publications about point cloud streaming in last year's MMSys in Paris. So this is my favorite representation because it is flexible, it's cheap, it's simple, and it is useful. Right? But the limitation is also very obvious. So as we zoom in the point cloud, we can see that we can observe many artifacts. For example, the host. Right? So one improvement to solve this problem is we can extend the 3D point when we do the rendering. Right? So we can kind of split the point into 2D plane, so that this split can cover the empty point, the empty areas generated from the point. So in 20 years ago, there's a guy, he proposed this method. So he tried to extend the point cloud to the elliptical Gaussians during the rendering. So this is how the Gaussian split looks like. So basically it's a split and it follows the Gaussian distribution. And after 20 years later, there's a guy, they tried to reconstruct the 3D world with 3D Gaussian splits. And they published their work in ACM-CIDRA 2023, and they received the best paper award. So their method is actually not related to our work. So they basically propose a 3D.js algorithm. So the input is set up to the images, and by using this algorithm, they can construct the 3D world using the 3D Gaussian split representation. So here is the example of what the 3D.js looks like. So this is a rendered image of 3D.js. And you can see that basically they're just a set of Gaussians, right? Ellipsoid Gaussians. And this is the center of each 3D space. Okay. So 3D.js is also a nice representation. So it's worse than point cloud, but still better. It's still good. So as a linear representation, it has actually photorealistic quality, right? So it is usually better than point cloud because we kind of overfitting the set of 3D Gaussians to mimic the 2D images. Right, so we can see that compared to other learning-based methods, it achieves the best. And meanwhile, it is also super fast in terms of rendering. So it is very fast compared to other learning-based methods, for example, Nerf. And the third feature is the best feature in our mind for the 3D.js. So it is an explicit representation. So it's not neural network. So I don't like Nerf actually. So I made a work in last year, also published in MMVE in Paris. So I tried to use Nerf to compress the point cloud. So, but I don't like Nerf because it is implicit. So it's just a set of neural networks, right? So it is black box. So we can do nothing to the black box. So it is not that cheap compared with the point cloud. So it's the best thing I think for 3D.js. It is explicit. It's just a set of Gaussians. Okay. So also the limitation is very obvious. So this is the common problem for the explicit representation. It's very large. So for example, for this scene, for this 3D scene, we need 6 million Gaussian space to depict it, and it usually requires over 1.5 gigabytes. So this is so I'm a streaming guy, so we always want to stream the 3D representation over the internet. So this is the classical framework or classical problem we want to solve. So now we have the virtual environment, the 3D world, represented by the 3D Gaussians. And then we want to stream it over the internet and show this virtual environment to the users. So the problem is that this virtual environment, this 3D scene, is extremely heavy, right? So we cannot do it in real time. And there are many ways to solve this problem. For example, we can do the scalable coding, or we can do the tiling and achieve the viewpoint adaptive streaming, right? So we also try to solve this problem using this kind of method. So this is the advertisement to our other works. So we try to build a layered progressive 3D representation for adaptive streaming, which is published in 3DE. And we also try to build a streaming system based on our representation. So this representation is called RPGS. So this will be presented on Wednesday by Eugene again. So in this work, we try to use a very straightforward method to solve this problem, compression. Right, so this work is about how we compress the 3DGS. But before we into the method, let's see why this method is only designed for MMSys. So I will show you why this method only works for this kind of things. Okay. So this video shows the rendering of the 3D scene. So and also the center of each step in this video. So we can find an interesting thing is that some splats they cluster along the structural boundaries. Then these structural boundaries they actually cover limited area. But the splats try to model these boundaries, they occupy over 70% of the model size. Meanwhile, some splats are sparsely distributed over the smooth area, and this smooth area covers a large and broader area in this 3D scene, but those splats only occupy below 30% of the model size. And we're wondering why. So this is related to the 3DGS training. So in order to generate the 3DGS with more photorealistic quality, the author designed something to kind of achieve this photorealistic rendering effect. So what the author designed is he introduced one more step during the training of 3DGS, which is called densification. So the idea of densification is very simple. We want to densify the splats for the fine details, and they design basically two rules to do the densification. One is if the splat is too small, then we clone it into two to fill the area. And if the splat is too big, then we split it into two to fit the area. Right? So because of this densification step, the trainer tends to add much more splats into the high frequency area, especially for the object boundaries or the edges. So this video shows that I record the video during I train the 3DGS to modeling a cube. So we can see that, so let's look at the boundary of the cube. We can see that the densification happens frequently, right? In order to generate more splats to depict the sharp features from the boundary. Okay. So now we have the observation and we know the reason. We start to think about how can we utilize this feature. So then we come to our method, which is called sketch and patch. So this is the painting. So before we go to the method, let's see this example. This is a painting, and we all learn how to draw a painting when we was a child, right? So usually the common step is we first sketch the outlines, and then we patch the border areas, right, which is sketched by the sketch. And we find that it is very similar to what we observed from the 3DGS, right? So inspired by the painting technique, we also try to categorize the splat into two kinds of splats. So one is called sketch splat, which is used to depict the boundary, which has usually high frequency features. And these sketch splats are usually semantic scaffolding. And another kind is called patch splats, which is used to depict the smoother and broader regions. Okay. So for the sketch splats, they are usually densely populated, like we see the demo previously. And they try to depict the boundary defining feature. And we find that it is interesting that those sketch splats are linear, usually are linear or perlinear. And they're error tolerant, so there are a lot of splats over the boundary, so it will be said that we just threw away some splats, right? We want to affect the visual quality. Then what we try to do is, we try to encode those sketch splats with some parametric models. And then we can save the model size. Meanwhile, we can achieve not bad quality and semantic information. So this is an example. So I extract the sketch Gaussians from this 3D scene. And it is about 400 megabytes, right? And then I encode those sketch splats with polynomial regression. So this is a very simple model. I only need 7 megabytes to store the parameters from polynomial regression. But still, it achieves the similar quality with the real model. Okay. So as for the patch splats is generated to depict the smoother features, and they are usually a sparse model, right? So this is the example of a patch splat. And it will be very straightforward for us to think that so now that the patch Gaussians, the patch splats are used to depict a broader flat area, right? Then why don't we just use fewer Gaussian splat to depict this area, right? So the first step we propose is we prune the patch splats. So we have a fewer number of patch splats to depict the broader area. But the problem is that once we move away several patch Gaussians, then there will be some holes, like the similar problem of point cloud. So it is very error sensitive. So that's why we introduce another step called optimization. So we change the size of the patch splats and ask them to cover the region again. Okay, so that's our method. It's very simple and straightforward, right? So we categorize the Gaussians, the splat, into two rows. One is called sketch splats, and we use the parametric models to encode the sketch splat. And then for the patch splat, we prune and optimize them to save the model size. And at the end, we will have this kind of hybrid representation with the parametric models and the pruned and optimized patch splats. Then we can store or transmit this hybrid representation to save the model size. Okay. So now let's see how good our method is. So we test our method for 3 things. So they are called Playroom, Dr. Johnson, Room, and Trap. And we use PSNR, SSIM, and LPIPS to validate the effectiveness, the performance of our method. Okay. And then we compare our method with 3 methods. So the first one is called baseline. We change the densification threshold of 3DGS to control the model size. And the other 2 are about the ablation study. So I won't show you the result of ablation study, so I just give it to save the time. Okay. So this is the RD curve for the scene Playroom. So the first one shows the trade-off between the model size and the PSNR. And the second one is the model size versus the LPIPS. So we can notice that at the same model size, our compression method can achieve improvement up to 3.2 dB on PSNR or 20% on LPIPS. So, and at the same visual quality, we only need 9% of the model size, or the 8% of the model size for the similar quality on PSNR and LPIPS. Okay. So this is the visualization. So the left one is the compressed one, and the right one is the ground truth, the raw model. right? So they all have the similar SSIM, which is 0.91, but our method only need, so after our compression, we only need 50 megabyte to achieve the similar quality. Okay, so actually you can see that this is the first step of our method. Right? What we do is just we categorize them into 2 rows and then do something separately. And also what we do is very simple. For the sketch, we just use the polynomial regression to model them, and for the patch, we just prune an optimal. So especially for the patch Gaussian patch splats, our method is very simple. So actually there are thousands of 3D compression methods now, so posted in archive. So it is definitely fine for us to use those compression methods to further compress the patch splats, and we can achieve better result in terms of the compression ratio and visual quality. And another problem is, this is also the kind of the problem for 3DGS itself. So currently what we do to validate the performance of our method is we project the 3DGS into 2D images and then measure the 2D metrics. But actually we're talking about streaming, right? So in the user scenario, the user always like wearing a VR devices and explore the 3D world. So the interaction is very important. So the further improvement for the evaluation is that we need to consider space and view consistency. Right? We need to consider the user's behavior, and we also need to consider the consistency between the space in the space size. And I will also discuss about this question in the doctoral symposium, which will be held on Tuesday. Okay, so that's all for my presentation.
Someone else there?
Thank you.
This is the
I was wondering about the time complexity. Yes, like how long it takes to create a rendering with 3DGS, just 3DGS versus with your hybrid representation.
Yes. So because you can see that we introduced basically 2 steps to do the compression. One is we use the polynomial regression and parametric models to model the sketch depth, and another one is we prune and retrain the splats from the test splats. So there are basically 2 overhead introduced. As for the parametric models, we can definitely achieve it in parallel. We can use the CPU parallel programming or the GPU to speed it up. And as for the training for the patch splats, it can be done also very quickly because we just need to slightly change the size of the prune splats, so it can be very quick. So basically, we can just ignore the overhead cost by this step.
Okay, thank you.
What about the decoding side?
Sorry?
So that's the encoding side. What about the decoding side?
Decoding side.
Yeah.
Yes. So because the decoding side, the overhead we introduced is we want to decode the splats from the parametric models, right? So you can just imagine that the input is the XYZ position of the splats, and output is the different attribute from the splat. So it still can be very quick. The overhead is caused by the polynomial regression. Right, it's very quick, just weighted sum.
So it's negligible on the decoding side.
Mm-hmm.
Right.
Thank you for a beautiful talk. It's, my question is just about mainly the same thing. So the parametric models, you didn't quite get into the details of those. You encode the attributes and the place where, I mean, these sketch splats, in the original form, they have an attribute, a color, right?
Yes.
And they have a scale.
Yeah.
The way I understand this is a function, but you didn't actually show, on that one slide, you didn't show the sketch splats in parallel to the parametric models. You just showed the sketch splats. You know which one I mean? 27 or so, something like that. So where you
You mean the side to side?
Yes, on the right hand side. So my question is, how does the parametric model actually look like?
So this is just a polymer regression. So what we do is, for each attribute for the 3D-GS, we build one polymer regression function. So for example, if for a splat which has 6 attributes, then we build 6 functions for the splat.
And the scale, I mean, they are not infinitely small, the splats, right?
Yes.
So you make them very small, right?
You mean in terms of the size? Of
Yes.
the splats?
Yes, because I mean, the way you showed them, they still have some scale, right? So they.
Yes. Yes, so it's about how we look for the scale splats. So we introduce a tedious set of methods to find the scale splats. So I didn't show it in the presentation.
So I just want to. My question is similar to his question. When you say very quick, are we talking real time? Are we talking milliseconds? What's the number we could do very quick?
Yes, so we did some experiment after this paper. So we noticed the problem from the reverse comments. So we tried to make the modeling in real time by using the parallel programming. So the result shows that I forgot the exact number, but basically it's below a second.
Oh, okay. That's very good. Yeah. Thanks.
One more question here.
When you use the technique to encode functions, on the decoder side, there is an encoding error or a translation loss. Do I need to do anything extra to recover?
We didn't consider this problem.
Okay.
And another point is that this polynomial regression, this is a very easy, very simple function. So we can take care of it if we want to do so.
Thank you.
So, 10 seconds. And the next presentation is acceptable latency in predictable first-person VR cloud games by Carsten.